Hello. We've looked already at image artifacts. Now let's take a look at artifacts that affect Doppler information. Not surprisingly, some of the grayscale artifacts also affect Doppler signals. In the upper left, we have an example of a mirror image artifact. There's a strong reflector immediately deep to the vessel, and this has caused a mirror imaging of the color display. In the lower right, we have an example of shadowing affecting both the grayscale image and also the color Doppler information. If I tried to get a Doppler signal using pulse Doppler from within that shadowed region, I wouldn't be able to get any signal. So these are just two examples of grayscale artifacts that can affect Doppler information as well. Here's an example of the single most important artifact affecting pulse Doppler, and it does also affect color Doppler. It's known as frequency aliasing, or just aliasing for short. It describes what happens when the Doppler shift exceeds the limits of the display. In this case, the peaks are hitting the limit of the Doppler display, the spectral display, and they are cut off. The cut-off portion, as you can see, wraps around and appears to come up from the bottom of the display. So it hasn't disappeared, it has simply been displaced. Now, one of the advantages of the spectral display is that it's very easy to recognize when this artifact is occurring. In this case, the aliasing is not very severe, and it's quite possible to fix it by simply shifting the baseline. So here on the right-hand side, I have moved the baseline down to the point where there is no longer any aliasing. The waveform no longer reaches the limits of the display. In fact, I've moved the baseline so low that there's very little display space below the line, and virtually all of the display is allocated to velocities above the line, or Doppler shifts above the line. So I've got rid of the aliasing by simply moving the baseline. Here's a diagram illustrating what the machine actually measures when it does the spectral analysis. So it detects Doppler shifts. It can measure up to PRF on 2, which you remember is the Nyquist limit, above the baseline and below the baseline. So for flow towards and away from the probe, the upper limits of measurable Doppler shifts are the Nyquist limits, half the PRF. Here on the right-hand side, I show what happens when the baseline is shifted. I've given a specific example here where we move it down so there's only 1/8 of the PRF range below the baseline, and that means there must be 7/8 of the PRF above the baseline. Notice, with the green arrow, I'm highlighting the fact that the overall range from the bottom of the display to the top of the display is always going to be equal to the PRF. This highlights the fact that varying the PRF will automatically vary the vertical scale of this display. So when you change the velocity scale on a Doppler instrument, you will be altering the Doppler PRF. It's not always possible to completely get rid of aliasing by just simply shifting the baseline, and therefore we need to look at other techniques as well. The second thing that we can try is to increase the velocity scale. So we can shift the baseline. If that's not enough, we increase the velocity scale. And in fact, it's normal, good practice to do both of those things to optimize the display of the Doppler signal. Another thing we can do, which is probably less obvious, is to reduce the ultrasound frequency. The Doppler equation tells us that the Doppler shift is proportional to the ultrasound frequency. So for a given velocity, if I reduce the ultrasound frequency, the Doppler shift will be lower, and therefore aliasing will be less likely. Another thing that I can potentially do is to reduce the distance between the probe and the point of measurement. You may be able to do this by using a different window into the tissues. Or, of course, you may achieve it by using an invasive probe. For example, using a transesophageal probe to look at the heart. If you are closer up, the machine can use higher PRFs, and therefore it can have a higher velocity scale. Theoretically, at least, you can increase the Doppler angle. Increasing the Doppler angle, you may remember, decreases the Doppler shift, and therefore will reduce or eliminate aliasing. Now, this is not always practical, and it's not always desirable from an accuracy point of view either. So it's not a very common tactic that you can use. If you are doing echocardiography, you always have the option to set aside the pulse Doppler and use continuous wave Doppler instead. However, for other types of machine, for general machines, CW Doppler is not available as an option. There is one last option though, which I've listed at the bottom here, and it's generally referred to as high PRF mode pulse Doppler. What happens here is that you force the machine to increase the velocity scale beyond the normal limits. Now, by the normal limits, I mean the limits set by the requirement that the machine should wait for all echoes to return before it transmits again. That's necessary to avoid range ambiguity. High PRF pulse Doppler means that you're forcing the machine to break that rule. So the machine will be transmitting again while echoes are still coming back from the previous pulse. This is going to cause range ambiguity, but it does increase the velocity scale further and therefore can reduce or eliminate aliasing. Let me show you an example. Here we've got a color image of a main renal artery. Pulse Doppler is looking at that region where the colors are dramatically fluctuating. And we can see from the Doppler signal in the spectral display that we have a dramatically abnormal signal. Everything has been done to maximize the ability of the machine to detect this signal properly. So the scale's been increased to the maximum, the baseline has been shifted all the way to the bottom of the display, but still we can't see the peaks of this waveform. So the operator has to invoke the high PRF Doppler mode that I mentioned before. So here on the right-hand side, we have an image that's now been able to correctly display the Doppler signal because now the high PRF mode is being used. Just take a look at the vertical scale. In the upper image, on the left, the scale goes up to about 200 centimeters per second. In the lower right, the vertical scale on the spectral display goes up to about 5.5 meters per second or 550 centimeters per second. So you see we've radically increased the velocity scale, and now we can see the peaks, which I see the machine has measured as being around 380 centimeters per second. Notice, by the way, how completely filled in this waveform is as well. So we have very high velocities, and we also have extreme spectral broadening, which fills in the waveform. These are the two hallmarks of stenotic disease: increased velocities and increased spectral broadening filling in the spectral waveform, and that indicates that there's chaotic and turbulent flow. I mentioned that the use of this high PRF mode does have a penalty, and that is that it introduces range ambiguity. Have a look at the grayscale image on the right-hand side, and you can see I've placed an arrow, a white arrow, highlighting the fact that there is a second sample volume, very superficial, and that's in addition to the desired sample volume, much deeper, which is acquiring the signal of interest. So the use of high PRF Doppler has introduced an unwanted second sample volume. Is this a problem? Not really. We're looking at extreme abnormal high velocities. That superficial sample volume, if it does happen to pick up significant Doppler signals, they're going to be very much lower in Doppler shift. They're not going to interfere in any way with our ability to see and measure the signal coming from the stenotic portion of the renal artery. So there is no practical problem with this, which is why this technique is commonly available. This is just a diagram to explain to you how the range ambiguity comes about. On the top left, we have the normal mode of operation, where we have transmit pulse, the range gate. The machine waits until all detectable echoes have gone, and then it transmits again. Now here on the right-hand side, I'm showing what would happen if, for example, I doubled the PRF. So I've doubled the velocity scale, which has caused the PRF to double. Now you can see the machine is transmitting again before the range gate has actually occurred. So we have the first pulse, and then the machine has to wait a time t1 before it range gates. However, the machine has transmitted a second time, and the range gate is occurring a shorter time interval after that second pulse. The machine is obtaining echoes when it range gates from both the first transmit pulse with a delay time of t1 and from the second transmit pulse with a delay time of t2. So in other words, there are two different sample volumes at two different depths. Now we come to a completely different artifact. This was discovered by a sonographer doing a higher degree. It initially met with significant skepticism, but subsequently he was proved to be absolutely correct. I've obtained this signal using what's called a string phantom. This is a moving string phantom used for testing and demonstrating Doppler instruments. So the idea is there is a thread moving in a water tank. The machine places the Doppler sample volume on that thread and looks at the echoes scattered from it. When the thread's moving, those scattered echoes will be Doppler shifted. So it's essentially an ideal target, a single moving object moving with a single speed. In this case, I've programmed the motor so that the velocity starts from a minimum, ramps up linearly to a maximum value, and then back down to a minimum value, back up again, etc. So we have just a simple time-varying velocity. Now, when we think about the fact that this is a single moving object, you might think that there would be a single Doppler shift at each moment, and therefore that the Doppler spectrum might look rather like this diagram. But let me show you what the Doppler spectrum actually looks like. You can see the substantial broadening of the spectrum, spreading of the spectrum above and below the true value. You'll also notice the amount of spectral broadening varies with the speed of the thread. So when the Doppler shift is small, the spectral spreading is small. When the Doppler shift is larger, the spectral spreading is larger too. Now, this is a problem for two reasons. One is that it may be confused with physiological spectral broadening related to disease, but more importantly, it affects the accuracy of measurements. On the left, we have what we would measure in an ideal situation. So if there was no spectral broadening, when we measured the upper edge of the spectral display, we would get the measurement I've shown with the blue line. The reality, of course, is that we have that spectral broadening, and therefore when we make measurements from the peaks of the spectral waveform, we get a measurement that is substantially higher, as I show with the blue line on the right. So the presence of spectral broadening is automatically going to cause us to overestimate velocities. Why does it happen? As usual, it relates to assumptions and idealizations that are necessary in order to make the measurement. On the left-hand side, we see what's displayed on the screen. We have the probe, we have the beam indicated with a single straight line, we have the sample volume sitting in the selected point, in this case I'm showing in the center of a vessel, and then we have the flow direction, which the user indicates with the angle cursor. The machine then calculates the angle between the flow direction and that beam, and it therefore knows the Doppler angle. On the right, I'm showing the reality. The focus beam is obtained by using an aperture, an area on the face of the probe to generate the transmit pulse and to receive the echoes coming back again. So we have all of the transducer elements, a group of transducer elements forming that aperture. And every one of those elements transmits and receives. So in fact, the ultrasound travels along a whole lot of different pathways to get to the sample volume. I've drawn a few of these pathways in the diagram. You can see that each one of those paths has a different angle relative to the flow direction. So we have a range of different Doppler angles, and that's why we get a range of Doppler shifts. You can see, of course, that the larger the aperture is, the more pronounced this problem will be. The thing that the manufacturers have done to address this issue is that when the machines are doing Doppler measurements, the aperture is reduced. The other major thing you can do is to try to be as consistent as possible. So when you're making a measurement in a particular vessel, for example, the carotid artery, you should have a protocol that specifies what Doppler angle you should use. And very commonly, this will be approximately 60 degrees. So as long as you consistently use a Doppler angle of around 60 degrees, the spectral broadening will be the same each time, and therefore you should be able to get consistent measurements. Furthermore, if you use diagnostic criteria that have been obtained under similar conditions with similar equipment, the intrinsic spectral broadening will be factored into the design of those criteria. So the criteria are effectively taking into account the presence of the spectral broadening. Now here's a particular example of intrinsic spectral broadening. It's referred to as the spectral mirror artifact because the waveform is symmetrical above and below the zero flow baseline. So we have apparently equal amounts of flow towards the probe and away from the probe. I've overlaid on the image a guess at what the aperture size might be and therefore what the range of different pathways that the ultrasound must be travelling. And you can see that there are a wide range of different angles relative to the flow direction. Furthermore, for half of those paths, flow will be towards the probe, and for the other half, flow will be away from the probe. So when the centre line of the beam is perpendicular to flow, we will get a symmetrical waveform like this. Here we have an example of aliasing in a colour Doppler image. We're looking at a vessel which is carrying flow away from the probe. So you'll notice that the colour should be red, orange, yellow, and you'll notice the colour bar has been inverted so that that particular colour means flow away from the probe. So the flow is going from left to right. Notice though, in the area that I've highlighted in the circle, for example, that we get a jump in colour from yellow, which is at the very bottom of the colour bar, to the pale blue colour, which is at the very top of the colour bar. This is obviously physiologically impossible. You can't have flow at high velocities in one direction and then immediately adjacent to that high velocities in the opposite direction. So it is clear when you have this sign, when you're jumping from one end of the colour bar to the other in adjacent pixels, that it must be aliasing. It is possible sometimes to have areas within a vessel where the flow is going in the opposite direction. But in that case, the velocity is going to be low. So we would have an area of red and then probably an area of black, and then adjacent to that, an area of dark blue. So we'd have dark red, black, dark blue. That would be a genuine flow reversal. But jumping from the maximum in one direction to the maximum in the other direction must be aliasing. Indeed, this image on the right-hand side confirms that. I've shifted the baseline of the colour bar almost all the way to the top. So I now have very little display range in the blue direction, and almost all of the colour bar is allocated to the red, orange, yellow, in other words, the flow away from the probe. Now you can see I've eliminated that aliasing, and we have proper display of the Doppler shift from that vessel. So let's summarise. Doppler's affected by a number of artefacts. Some of these are the same artefacts as for grayscale imaging. But in addition, there are Doppler-specific artefacts. Examples of this, and the most important of these, are frequency aliasing and intrinsic spectral broadening. I've also mentioned spectral mirror artifact, which is a special case of that spectral broadening. Now, there are some other artifacts, and we'll cover those in the next lecture, and those are artifacts due to incorrect control settings. So we'll take a look at that in the next lecture.